Welcome to Ask and Learn.
We are given information in this problem and a diagram to describe a gas phase reaction between two different gases, X and Y. We are given color codes for finding which one of these particles corresponds to X, Y2, XY, and Y. And we are told in words what the reaction is between these so that we can write it out as X plus Y2 goes to xy plus y. In part A, we are told that the equilibrium constant Kp for this gas phase reaction is equal to 4.5. And we want to know which one of the molecular scenes we are given, 1, 2, or 3, corresponds to this reaction being at equilibrium. We can write out the equilibrium expression Kp using this equation that we have written out. We know that we need to have the partial pressure of each gas in the product side raised to its stoichiometric coefficient. And we need to multiply that value for each gas in the products and then divide by those same quantities for the gases on the reactant side. So all of the stoichiometric coefficients in this equation are 1. So we just have to examine the partial pressure of each gas in the products, multiply them together, and divide by the partial pressure of each gas in the reactants and multiply them together. We are told that the partial pressure for each one of the gases is equal to 0.10 atmospheres. And so for each one of the molecular scenes, that is 1, 2, and 3 in the diagram, we have to go through and count how many of gas X, Y2 gas, XY gas, and Y gas that we have based on the color scheme that we are told in the problem. However many of each one of those molecules we see in the diagram, we can multiply by 0.10 to get the total partial pressure of the gas in that specific molecular scene. And when we do that, we can form the reaction quotient formulas for each one of those expressions and determine, after we perform the division, which one of them is equal to that equilibrium value of 4.5. So we start with Kp. We know that from this expression, it would be the partial pressure of the product, so XY gas, times the partial pressure of Y gas, divided by the partial pressure of X times the partial pressure of Y2. And we know that at equilibrium, this is equal to 4.5. So now if we look at the diagram in the first one, and we count first the number of XYs that we see, and the XYs in the problem are one orange atom bonded to one black atom, and we multiply the total number that we see for those by 0.1, we see that there are 4 of them total. So when we multiply that by 0.1, we have partial pressure of XY in the first scene of 0.4 atmospheres. These are all pressure units that we can say are atmospheres, so I'm not going to write out the unit every time, but you can if you want to. And then we move on to the next term, the number of Y gas particles. So how many of those single black atoms do we see in that molecular scene? Then we multiply the total number that we see by 0.1. We see that there are 2 of them, so that comes out to partial pressure of Y of 0.2. Then we divide that by the number of X, so the number of the single orange atoms that we see in that scene, and that comes out to 0.1, since we would find that there is just 1 of those. And then the partial pressure of Y2 is how many of those 2 black atoms that are bonded together to form that diatomic Y2. and there's just one of those. So that's 0.1 atmospheres. Then we just find that ratio, and we see that it has a value of 8. And this is not equal to the equilibrium value of 4.5, so we therefore know that the molecular scene in the first given diagram is not at equilibrium. We use that same method to go through and solve for Q2 and Q3. So again, when you count up the number of each one of these molecules in 2 and 3 and multiply them by the partial pressure of 0.1 atmosphere, you should get, for Q2, 0.2 times 0.2 divided by 0.3 times 0.2. And that should come out to about 0.67, which again means that this is not at equilibrium since it's not equal to 4.5. Finally, for Q3, you should get 0.3 times 0.3 divided by 0.2 times 0.1, and it turns out that this does come out to 4.5. And so since that matches the equilibrium constant value of 4.5, we can conclude that the molecular scene in the third diagram is the one at equilibrium out of the three. Now, part B, we want to have a ranking for the highest change in Gibbs free energy down to the lowest. So this is a highest delta G, and this is the lowest delta G between the same three molecular scenes that we were shown for part A. And in order to determine that, we have this equation where we can compare the values of Q and K. We know that K is always 4.5. And we calculated values of Q for 1, 2, and 3. And so based on this, we can see that if Q is greater than K, then that means that delta G will be greater than 0. The reason for that is that if Q is greater than K, then this denominator value is greater than the numerator to make that ratio come out to be less than 1. When we take the ln of a number that's less than 1, it becomes negative. But with this negative sign out in front, that will be a positive value. Likewise, if Q is less than K, then delta G is less than 0. And if Q is equal to K, then we are at equilibrium and delta G equals 0. So now if we go through, starting with the first molecular scene, we see that Q is 8 and K is 4.5. So for the first one, we say that Q is greater than K. And when Q is greater than K, delta G is greater than 0. So all we can say qualitatively right now is that we know delta G is greater than 0 for the first diagram. Going on to the next one, we see that Q 0.67 is less than K 4.5. So Q is less than K this time. And we know that that means that delta G is negative. So delta G is negative, and because of that, we can say that delta G for the first one is greater than the second one, since the first one's positive and the second one's negative. Finally, for the third one, we know that this is at equilibrium, so Q equals K. And so delta G equals 0. So we can say that 3 is greater than 2, since 2 is negative and 3 is 0, but 3 is less than 1, since 1 is positive and 3 is 0. So when we write that all out for our ranking, We have 1 has the highest delta G since it's positive. That has a greater delta G than 3, which is at equilibrium and has a delta G value of 0, which is greater than the lowest delta G, or the only negative delta G, which is present in diagram number 2.